Hello, this is Dr. Reena Rani Ray. Today I will discuss about a wonderful group of microorganisms known as Archaebacteria. Living organisms may be divided into prokaryotes and eukaryotes. Prokaryotes include bacteria, that is Monera, and protista, that is protozoa. Eukaryotes include the fungi, the entire animal kingdom and entire plant kingdom. Archaebacteria, this kingdom lies between the prokaryote and the eukaryotes. The phylogenetic tree of life, they show that Archaea originates from a different offshoots from that of the bacteria, and they show greater affinity towards eukaryotes. They are found in extreme conditions, so they are viewed as extremophiles. They live in harsh environments like volcanoes, the deserts, and the ocean bottom. In the year 1977, the scientists Dr. Carl Weiss and Dr. George E. Fox, they recognized Archaea as a completely independent, different kingdom. And this kingdom includes three groups, namely Euryarchaeota, Prenarchaeota, and Porarchaeota. The size of Archaebacteria ranges from 0.1 micrometer to over 15 micrometer in diameter. They occur in various shapes like spheres, rods, spirals, plates. Archaea means ancient. Initially, people used to think that Archaea are just the bacteria, but there are certain differences which make them separate from bacteria. The first uniqueness lies in their outer wall structure. Structurally, Archaea are most similar to gram-positive bacteria as they have outer cell membrane and cell wall. Cell wall is semi-rigid that helps to survive in extreme condition and does not contain peptidoglycan. Only methanogens have a layer of pseudopeptidoglycan or pseudomoraine, where the sugar residues, namely N-acetyl-glucosamine, that is NAG, and N-acetyl-talosaminuronic acid, that is NAT, are linked by beta-1,3 linkage. That is why the cell wall of Archaea is insensitive to lysozyme. Archaebacterial cell membrane shows ether-linked lipids. This is very important, whereas a eubacterial cell membrane shows ester-linked lipids. This is the characteristic feature of Archaebacteria, which acts as a biomarker for their detection. Archaebacterial lipids have some uniqueness. Their hydrocarbon chains are normally the C20 phytene or the C40 biphytene. However, a small amount of C25, 30, 35 isoprenoid hydrocarbons are occasionally found. In the Thermoacidophiles, 1 or 2 cyclopentane rings also commonly occurs in C40 chains, which make them resistant to high temperature. Archaebacteria reproduce asexually by binary fission, fragmentation, and all the species of Archaea have the same genetic material. The RNA polymerase of Archaebacteria is made up of 8 to 12 subunits, while the eubacteria is made of only 5 subunits. Let's have a very quick look about the differences between bacteria and Archaea. Regarding the cell wall, peptidoglycan and the lipids of the membrane, that is long-chain fatty acids, those are absent in Archaea but present in bacteria. Carbon linkages of lipids is ester in bacteria, whereas ether in Archaea. Long-chain branched alcohols bound to glycerol is absent in bacteria, but it is present in Archaea. Phosphate backbone is of glycerol 3-phosphate type in bacteria, whereas glycerol 1-phosphate type in Archaea. In both bacteria and archaea, the chromosome is circular type, but introns are present just like eukaryotes in archaea. Replication, transcription, translation, all are eukaryotic-like in archaea. So there are 3 RNA polymerases in archaea, whereas only 1 in bacteria. Ribosomal proteins are present in archaea but not in bacteria. tRNA contains thymine in bacteria. Regarding their nature, the bacteria are parasitic in nature and causes disease, but archaea are free-living. Bacteria can be categorized as gram-positive and gram-negative, whereas archaea can be Methanogens, Halophiles, and Thermoacidophiles. Bacteria can tolerate temperature about 100 degrees centigrade, but archaea are famous for their high temperature tolerance, and archaea are not killed by the antibiotic. There are some weird things about this kingdom. They can survive high doses of radiation, that is radioactivity. They can survive under rocks and in ocean floor vents deep below the ocean surface. They can also tolerate huge pressure differences. So we can find them in the hot springs of Yellowstone National Park, in the Dead Sea, and in the salt bed. Now we are coming to the halophiles. It literally means salt-loving. But these organisms are not just salt-loving, but they require salt as high as 17 to 23%. Just imagine, seawater contains only 3% salt. This is a diverse group of archaea present in highly saline environments like salt lakes, solar salt evaporating plants, and brines. The common specimens are Halobacteria and Tetragenococcus halophiles. Their colonies are red to orange in color due to the presence of carotenoids, and these carotenoids protect them from the damaging effect of sunlight. All species of species are chemo-organotrophic. That means they use chemicals as their energy source and are strict aerobes, but few species are anaerobic in nature. Now we are coming to the methanogenic bacteria. As the name implies, they can produce methane, but in absence of oxygen. They are found to be present in the marsh gas in wetland releasing. They are present in stomach of ruminants. They are strictly anaerobic organisms and are very sensitive to the presence of oxygen even at rest level. They exist in both gram-negative and as gram-positive categories. Some are mesophilic while some are thermophilic. Some methanogenics are rods or cocci, spirally short rods or filamentous in nature. Methanogens are further grouped into 8 major groups containing 18 total genera. Some noteworthy specimens are Methanobacterium, Methanosarcina, Methanospirillum, etc. Thermoacidophilic bacteria are the next group. As the name implies, they love heat, they love acid, and so they are found in the deep sea hydrothermal vent and also in the Yellowstone acid pool. It's a heterogeneous group of organisms which have the ability to grow at high temperature and low pH, that is at highly acidic conditions. They are gram-negative. They are divided into 3 groups: sulfobolus, thermoplasma, and thermoproteus. The first group is the sulfobolus. They're present in hot springs and soils. They're spherical or lobate in appearance. They grow in pH 1 to 4 and at a high temperature of 70 to 87 degrees centigrade. Their cell wall is made up of lipoproteins and carbohydrates. They use elemental sulfur as their main substrate, thus growing as chemolithotroph. So they are present in the hot springs, and the noteworthy specimen is the sulfobolus acidocaldarius. Thermoplasma. They are found only in the piles of burning coal mines, which may contain traces of coal and iron pyrites. They oxidize the iron pyrite, thus forming acid and heat, and creating an environment suitable for their growth. Their optimum temperature range is 45 to 65 degrees centigrade and pH range 0.8 to 4. They are facultative anaerobes and can use mono and disaccharides as their energy source. They possess flagella for motility. And known samples, the Thermophilus acidophylla. Last group is the Thermoproteas. They are found only in the geothermal areas of Iceland. They are long, thin rods, up to 80 micron in length. They are bent at the middle and forms a V shape. The temperature required for their growth is 78 to 95 degrees centigrade and a low pH of 2.5 to 6. They are aerobic and can use sugars, alcohols, and organic acids as energy sources. Thermoproteus tenax is a notable sample. There are certain applications of this magnificent group of organisms. They can be used in the PCR for the DNA polymerase, rather than thermostable DNA polymerase extracted from Pyrococcus furious is used for PCR. In industry, their thermostable enzymes can be utilized. Methanogenic archaea are a vital part of sewage treatment. Acidophilic archaea are used effectively for the extraction of metals from ores, including gold, cobalt, and copper. And archaea host a new class of potentially useful antibiotics, which is known as archaeocin, which have a novel mode of action. So this is all about the magnificent group of organisms. And so thank you for your patient hearing.